Hi all, my name is Juan Paredes, and today in Lecture 4 we'll be treating the subject of solving ODEs with Matlab and Simulink. First, let's go over ordinary differential equations, which we'll refer to as ODEs from now on. Let t represent the time, and let it be greater or equal to 0. Then let x and u be vectors, and let tf represent the final time. So, for all t within the time interval of 0 and the final time, we'll obtain x in time, given an initial condition for x, knowledge of u at all times, and supposing that the system dynamics are given by the derivative of x with respect to time, which will be represented by a function of time, x, and u. Since our focus is on linear time invariant models, then the equation above can be represented as such, where A and B are constant matrices of proper dimensions, and as you may recall, this is also called the state space representation. We'll learn how to numerically solve this sort of ODEs using both Matlab and Simulink. Both Matlab and Simulink offer several resources in order to perform this sort of operation. However, we'll focus on these four. For Matlab, they'll be OD45 and LSIM, and for Simulink, we'll use the state space block and the integrator block plus a Matlab function block. For an example, we'll use a very simple linear ODE, which is represented by x dot equals to minus x plus u, where the initial value for x is going to be 2, and u is going to be represented by a step function. A step function is a function in which the value changes at a given point in time. For example, for t, for time between 0 and 1, the function is going to be 0, whereas for any time that's greater than or equal to 1 second, the function is going to be equal to 5. Now we'll solve this for all t within this time vector. And since we're assuming that the output is going to be equal to the state vector, we can use the following state space representation. A is equal to minus 1, B is equal to 1, C is equal to 1, and D is equal to 0. Before proceeding, I'd like to take some time in order to see these 6 points. These are going to make it easier to explain some of the details of Matlab and Simulink programming. First, the state space representation and the system output. As you may already have seen in class, x represents the state vector while u represents the input vector. However, the actual output of the state space representation is given by y, and hence the full system is represented as such. In most cases, the state vector is not going to be equal to the output vector. And so, in order to solve the whole system, since the second equation is algebraic, first we can solve the first one for x, and then we can use the second equation to obtain the actual output. Keep in mind that there are Matlab and Simulink functions that do both simultaneously. In this case, LSIM and state space block offer that sort of functionality. Numerical solutions and time intervals. We mentioned that we would obtain xt for all t within this time interval, as in 0 and the final time. However, since our focus is in numerical solutions and these have inherent restrictions, then we can only obtain solutions at discrete points in time. That is, at start and end points of time intervals within 0 and tf. For example, we can obtain xt for all t within 0, ts, 2ts, and so on, where ts is a fixed size of the considered time intervals, that is a step size. And keep in mind that you can make ts small enough to have a smoother plot and maybe a greater solution accuracy. However, if you decrease TS too much, that will increase the computational load, which means that you will spend more time simulating the whole system. Now, we need to make a distinction between fixed and variable step. Fixed step solvers keep the step size constant throughout the whole simulation, just like the last case we mentioned in the last state, as in TS being kept constant. However, variable step solvers change the step size during the simulation depending on how fast the system state changes. If the states change fast, then the step is going to be smaller, whereas if the state changes slowly, then the step is going to be bigger. This may lead to less time steps and less computation time, but it really depends on how fast the dynamics of your system are. ODE 45 is inherently a variable step solver, but it can be supplied a discrete time vector at which you require the states. That is, you can make it behave like a fixed step solver, which we will prefer in most cases. We will use a fixed step solver for Simulink. And for sufficiently small step sizes, fixed and variable steps offer similar degrees of accuracy. Again, for smaller step sizes, your simulation may take more time. So be careful on keeping the step size not too small. We'll see how to set this up once we get to the programming part of the lecture. Now, MATLAB function handles. This is important for ODE 45. Function handles are used in MATLAB to represent functions. For example, if you input this in MATLAB, then f is going to be a function handle for x squared plus y squared. And if you use f2, 1 in the MATLAB command line, then you will obtain 5. They can also be used to make certain inputs constant. For example, for given the function handle f, you can set g as follows, which would make the y input of f into a constant. And because of that, if you use g2 in the command line of MATLAB, then you'll obtain 8. A function handle can also be used to pass a function to another function. And this is important because we'll use function handles in order to pass differential equation functions to ODE 45. MATLAB dynamic system models. This is important for LSIM, and you'll probably use it for other functions such as body. Don't worry, you'll see this further down the line. For the moment, you should know that dynamic system models are used in MATLAB to represent systems that have internal dynamics or memory from past states. That is continuous time systems or discrete time systems. Don't worry about the discrete time system right now. Commands that yield dynamic systems include TF for transfer functions. We'll speak more about this later. And state space models like SS. Most MATLAB functions that analyze linear systems use dynamic system models, including LSIM and body, like I mentioned before. For example, if you input this command in your in the MATLAB command line, you'll create a dynamic system model SSIM, which is going to represent a state space system with matrices A, B, C, and D. Finally, I wanted to talk about the state space and transfer function representations. They can be both used to represent time invariant linear systems. However, they are quite different. As you can see in the last couple of equations, you can see how they can be made into one another. However, you should take into account that only assuming that time is greater or equal to 0 and that the initial condition is equal to 0, then for a given input, both representations will yield the same output. MATLAB doesn't offer an easy way of setting initial conditions for transfer functions. So we'll mostly use state space when the initial condition is different from 0. So as a reminder, this is the linear model that we'll use in our example. Very simple one. And yeah, so let's get on with it. Okay, so now we're in the Matlab workspace. Before starting to do anything, we're going to set some preferences, because right now the letters, the font size is a bit too small. So in order to address that, we go to preferences in the environment tab. We go from Matlab to fonts, and then we change this to a higher value. Let's go with 24, should be fine. And yeah, there you go. Bigger letters. You won't need to do that, but I'd like to keep it this way to show you everything in a better way. Anyway, let's go to new, and let's select script. This will create a new script. It's untitled 6, because I had 5 other scripts open before this, but for you it probably will be 1. Anyway, we'll start doing using free commands, which will be close all, clear all, and CLC. What these free commands do is basically clean most of the workspace in Matlab. First, close all closes all of the figures, clear all clears all of the workspace variables, and CLC clears the command window. Allow me to show you how these two work. So let's say A equal 1. Yeah, it prints A here, and it now I have a variable in my workspace called A with a value of 1. That being said, notice that if I use a semicolon here, it's not printed in the screen. It's going to be important for when we actually write in our programs, because we don't want to clutter the command window. So we'll usually end most of our commands with a semicolon. Anyway, first I go for clear all. This clears my workspace, and then CLC. This clears the command window. Be mindful of clear all, because clear all erases everything in the workspace, and if you wanted to use a variable from a previous program, then you're not going to be able to use it if you use clear all. In that case, you may want to have Matlab not run this line, so you can put percentage connotation here. And what this is going to do is let Matlab know that you should ignore this line. You can use this for both comments, or just to make sure that Matlab doesn't run certain commands. Anyway, moving on, as I mentioned before, we'll start with ODE 45. And because of that, we need to set up a function for the x dot. So let's go ahead and do that. First things first, function, which is used to declare a function. X dot, the output, is equal to ODE fun, which is going to be the name of the function. And we're going to say that the inputs are T and X. T and X are the inputs that you're going to need for ODE 45. So keep that in mind when you create other ODE 45 functions. So as we mentioned in the slide, we're going to make sure that x dot is described by a multiplied by x plus b multiplied by u. Right. But right now we don't have a defined, b or u defined. So let's proceed with that. X is one of the inputs, of course, so we already have that one covered. And as we said before, a is equal to -1, b is equal to 1, and u is the step function, and we'll define it as follows. Right. Okay, so what this function does is basically, this is 0 if t is less than 1, and this is 1 if t is greater or equal to 1. And so what this does is it allows us to create a very concise function for the step function that we want to represent. And then you multiply it by 5, which is the value of the step function. So now in here we have x, we have a, we have b, and we have u, and that we have already defined our ODE function. So let's go back to the main body. First, we need to declare the initial condition for x, which is going to be 2, as we mentioned before, and then we need the time vector, which is going to be from 0 to 10 with a step size of 0.01 seconds. In order to get this vector, we run the following function. And what this tells Matlab is that I want a vector that goes from 0 to 10 with a spacing of 0.01. I can show you this by copying and pasting this here in the command window. And as you can see, within each, in between each of the members, there is a 0.01 spacing. And here I have an ANS variable that contains it, because ANS is the default variable to which all of the values that you put in the command window are stored in. For example, if I put here 2, then it's going to be 2. If I put here when I press enter, it's going to be 1. Anyway, let's clear all again. Let's continue with this. And now we're ready to run ODE45. First, we want the output. I'll explain this in a while, don't worry about it. Oops. Okay, so this is ODE45. And the first input of ODE45 is going to be a function handle to the ODE function that describes the dynamics of the state vector. That is, x dot is equal to a function that has inputs t and x. And yeah, this is the function handle that we mentioned back in the slides. Then the second one is going to be the time vector. And this can be either the vectors at which, the time steps at which you want the solution to be obtained, or it can be just a vector that has two numbers. However, if you do this, the ODE45 is going to use the variable step solver to give you the time, the solutions at adaptive times. That is at times that of variable step. So you won't really have the solutions at this 0.01. That may depend on the dynamics of your system. So in order to make sure that we get the solutions at the time steps that we desire, we just let it know that we want the time solutions at each member of this vector. That is x at 0, 0.01, etc. And finally, x0 is the initial condition for the state vector, that is x0. In this case, x is a single value, so x, the initial one is value of x is going to be 2, as we said in the slides. And the output of ODE45 is first the time vector, which would make sense if this is just two values, since we want the time to obtain the times that ODE45 chooses. But since we already are giving it the exact times at which we want the solutions, then we can just use this to tell Matlab that we don't want it to be stored elsewhere. And finally, we have the actual solution at each of these time steps. So x contains the state vector. Now, as we mentioned before, this if we were solving a state space function, this would be a state vector, but this wouldn't be the actual output. So in that case, what you want to do is set the the C and D matrices, and then obtain the output by using xx plus d multiplied by, yeah, this will still run. Let's make sure this runs first. This will still be okay because this function can work with vectors. So, but keep in mind that your input might be different. So just be aware of that. Also, since d is 0, this is basically going to go to 0, so it doesn't really matter. Anyway, and finally, let's plot the whole thing. T comma y. That means I'm going to be plotting t on the x-axis and y on the y-axis. And just to make sure, let's say this is figure 1. You have different figures, you probably would say figure 2, and this would start a different figure. But for the moment being, let's give it a 1. Okay. So before running, let's save this. Let's say ODE 45 tutorial. And let's run it. All right. As you can see, here is the curve. And it's pretty nice, but it looks pretty barren. So let's try to change the shape of our resulting figure. First, let's see if I can increase the width of the resulting curve. We can. We just need to add the line width here and add a 2. And let's say that I don't want to run whatever is on top of here, since this is going to be the same result. So what you do is basically you put 2 percentage signs here, and this is going to create a new section. And if you so wish, you can create, you can press here run section, and it's only going to run everything that's below here or within two consecutive, section separators. Yeah, let's do this. And yeah, only the plotting is going to take place. Yeah, as you can see, this thicker line. Now let's put names to the x-axis and the y-axis. We can do this by using the function's x label. So let's say this is time. Let's use y label. Sorry. Let's assume this is y. By the way, this is anything that's between the columns is going to be known as character, and this is actually like a string. Okay, let's see how this looks. And yeah, you can see here we have y and here we have t. But this may be a bit too small for your liking, so if you want to, you can use a different option here called font size. Let's say 14. Do the same for y. Yeah, as you can see, the font size is increased. Now let's use another, actually, grid on. This just makes it look nicer, in my opinion. It creates a grid, and then you can see the values at each time in a better light. And now I'd like to introduce you to what's called LaTeX notation. In order to use LaTeX notation, you can use the interpreter option and use LaTeX. Initially, it's just going to make everything look nicer, in my opinion. Yes, you can see here, YT. But the true strength is when you actually use LaTeX to typeset mathematical notation. You can do this by putting $2 signs between characters. Put here. And as you can see, now you have a curve which is more akin to an actual variable. However, let's say that this y wasn't actually y, but phi. And you can see you can quickly put the phi symbol here. LaTeX is a powerful tool that you can use in order to use mathematical notation, and I encourage you to delve a bit more within it. And but if you want any a couple more of commands for LaTeX, then you can easily search them online. Now, let's say that I'm okay with what we've obtained here. So yeah, this is pretty nice. And let's say I want to put this on a report. We can go to here, export setup. Before that, let's go 600. That's just a preference, and this is just for the quality of the image. Then let's go to export. There are a couple of options here, but I like PNG. And then let's go to OD 45 figure. Yeah, like this. And then I wait a moment. Depending on whether or not this is your first image, it may take a while, but once you create a couple of images, it's going to be much faster. Okay, so I am back. Sorry, I didn't want you to waste your time seeing that, but now the whole thing has transpired. After it was after my figure was saved here, as you can see, figure.png. I have pressed OK, and this disappeared. Then you can close this, and then you can use this in whatever report you want. And so that's it for the OD45 function. Now let's try to use else if. Since we want to create a new file, we just click on here. I will create a new file. Again, clear all, CLC, oops, and close all. Anyway, we're going to want to reuse some of these files. For example, we're going to want to reuse this. And unlike the previous iteration, we actually need a input vector here at each of these time steps, or at each point in this time vector. So we say that u is equal to this function over here, which is going to be the step function. And after this, we set up a dynamic system. That's right, the same variable that we set during the that we mentioned during the slide of dynamic models. We're going to make this A, B, C, D, which is going to create a dynamic model with of a state space representation with A, B, C, D matrices, which I haven't yet defined. Not to worry, here they are. B is equal to 1, C is equal to 1, and D is equal to 1. No, D is equal to 0. A mistake. But anyway, as you may already be thinking, this function will be taken into account that there is a dynamic system and that there is an output function. So we won't have to explicitly calculate the output as we did before. Anyway, let's write the else function. Don't worry, I'll explain this after I am done. Okay, so here is else in, and the inputs are the dynamic model that we obtained here, the input vector, which whose size has to coincide with the input time vector, and finally we have the initial condition for the state vector. Now the outputs that we can get are the actual output, the state vector at each time that we use as input, and finally the output time, which again is going to be the same as t, so we really don't need it. Anyway, we can actually use the function that we used before to plot everything. So now we save it instead of OD45. Yeah, you can click on previous file to get its name, but instead of OD45, we're going to use LSIM. Save it. Let's run it. And now you see it's basically the same. Anyway, let's follow the same procedure as before. Yeah, this is another one that you may want to try, but for the moment being, we're not going to touch it. Let's apply this figure and then like export this. Again, click here, OD45, but let's change this to LSIM. Save. And now you see it's going to take a while. Not that much long though. You can see LSIM is already here. Then you press OK. And you close this, and yeah, that's it for LSIM. Now we'll move on to Simulink. In order to enter Simulink, you can either go to Home and press Simulink, or you can just type Simulink in the command window. Yeah, now you open the Simulink start page, and what you'll mostly want to do is create a blank model. So there we go. Here we have our blank model. But before doing anything, I'd like to go to the modeling page and go to the model settings. Yes, so here we can set up our start time and our stop time. This is okay since this is the start time and the stop time that we set up. And here we get to choose our solver. Now, as we mentioned before, we're going to go for a fixed step solver. And then we're going to choose one of these. Anyone above ODE4 should do the trick, but ODE4 is going to be more than you. It's going to suit most of your needs in this course. And finally, we check for the fixed step size. It's usually in auto. You want to change that for the actual step size that you would like. In our case, it's 0.01. Press apply. Okay. Now we can get started. All right, now let's go to the library browser, which will allow you to choose among other functions. And what you'll notice first that Simulink is a very graphical interface. That is, you can choose several blocks and use them in order to build your system. First things first, we need our input, which is going to be a step function, as we mentioned before. And here is a step function. So we get here. And we double click on every single block in order to set up its configuration. So here we have a step time, which is at 1 second. This is okay since we already, this is what we actually want. The initial value is 0, okay. And the final value is going to be 5, as we mentioned before. Sample time should remain 0, don't worry about it too much. Anyway, now we have to set up the model. And for that, we can go to the Continuous tab, and we can select the state space model block. Drag it here. And here we can set up, hold on, and double click on it to set up the state space model. First, this -1, this is 1, 1, and 0. Initial conditions, as we mentioned before, are 2. Don't worry about these two options just yet. All right, so the way in which Simulink blocks are connected is through arrows. This is going to be one of the inputs, as mentioned here. And this is going to be our system output. This is like LSIM in the way such that this performs both the dynamics function and the output function. So let's connect these two. You can click here and drag an arrow all the way to here. And that way we have set this step function as the input for this block. And now we want some way to visualize the output. So now we go to the browser as well. And go to Things, which basically gives you all of the options that you can in order to visualize how to send values to other places inside of the simulation. In this case, what we want is a scope. Okay, and yeah, right now we have connected because we put it nearby the output of this block. And what you can do here in Simulink is run this without having to save it, but this isn't recommended, so let's just save it. Yeah, see, new link. Sorry. Tutorial. Okay, now that it's saved, let's run this. And then we double click on the scope to see what we obtained. And yeah, as you can see, it's basically the same as the one that we obtained in the other cases. Now I want to explore some other options in which we can obtain the same response. First things first, I would like to show another way in which you can represent a step function so that you can see how this can be represented as well. So if you recall in ODE for defining LC, we use the time as an input in order to determine the step function. We can do this as well here. For example, we can go to sources once more, and we can go to the clock function, which is basically a time, a block that has time as the output. And in order to set up our step function, we can use an actual function. Let's go to user-defined functions, and we can set up our Matlab function. Okay, then we put it here, and now we have a Matlab function with an input of time and an output of the input of this state space function. By the way, since I copied this from here to here, this shares the same configuration. Keep that in mind if you ever copy on paste blocks. Anyway, if we want to change this, we need to double click here. And as you can see, this is a Matlab function. We can change this, for example, let's say this is U, and this is going to be T, and this is going to be step function. And just like before, U is equal to 5 multiplied by T greater or equal than 1. Okay. Now, if you want to go back to the Simulink function, you go to the editor tab and press on go to diagram. And as you can see, the block has changed to mirror the changes that I made in Matlab. The input is T, the output is U, and the name is step function. Let me save this as well. And let's run it again. All right, let's see here. Yeah, both are pretty similar, but if we want to make sure that they are similar, what we can do is plot this in a single scope. And we can do this by using a max. So let's say go to a signal routing tab, and let's get the max, which is going to allow us to put two signals in a single arrow, let's call it. Yeah, it goes here, this goes here, save as well, and run. And as you can see, one is in top of each other, so they're pretty equal. Just to make sure, we're going to see what happens if I put this as a 0. Yeah, there we go. Now they're different. And now let's put this as 2 once more. And there we go. And finally, let's explore a third option. For this one, we're going to be using this step as well. And for this one, we're going to use a user-defined block and a new block which we haven't seen before, which is going to be the integrator block. This integrator block performs integration over the variable that's in its input. So what we want to do here is basically set up the function to be our ODE function. We can do this by clicking here. Let's say xd is equal to ODE fun, or FCN, that's fine, t comma x. Or since we actually don't need time, we just make it x comma u. And in this time, we're going to make a equal -1, be equal to 1, and xd is equal to a multiplied by x plus b multiplied by u. And that's it for our function. As you can see, this is basically the ODE function, and u is going to be the step function, and x is going to be the input vector. Now let's keep it this for the moment being, and let's go back to our diagram. As you can see, because I set 2 inputs in the Matlab function, here now I have 2 inputs. First, the step function goes to the input, u, and now let x dot go to the integrator, which implies that what comes out of here is the integration of x dot over time, which is equal to x. And we'll put that as feedback on our ODE function. And that's basically it for us. And if we want to see whether or not this actually gets the same result, we can connect this as well. And let's see if this actually gets the correct result. And you can see that that's not it. And you know why that is. Because I haven't actually changed the configuration of the integrator. Double click here. And as you can see, the initial condition is 2, which is incorrect. We need actually for it to be 2. Okay, let's try this again. Sorry, I need to run it. Yep, presto. Now we have the free ways of calculating our ODE using Simulink. Just remember that this is the state vector, and the only reason why we can fit this and treat it as an output is because the state vector is equal to the output vector. If we, for example, had a different C, what we would have to do is basically, if we had an output function that's not y equals x, what we would have to do is go to the math operations, get a gain function, and multiply this. This would be C, this would be D, and then we would need to use a plus a summation function, and this would be oh no, this one's actually 0, and this would be the appropriate output. Again, there really isn't any changes, so it's going to be basically the same. So yeah, now we have seen 3 ways of calculating our ODE function. This is the state space block, and this is using the integrator plus the Matlab function block. Now let's compare all of the solutions that we have obtained in a single file. For that, first we'll want to create a new file, just so that we can keep this Simulink tutorial on its own. We'll call this plot, and then we'll erase this, create a copy of this. Finally, we will obtain one of these in the sinks, which is called to workspace. We'll get one for each signal that we want to get to the workspace. And so first we change the name to, let's say, sim1. Also make sure that you are using an array. It's much easier to manipulate during Matlab. Okay, let's connect this here, and now let's give them names. Actually, Matlab doesn't like it when everything has the same name, so now we have to use first call these different names. Yeah, sorry about that. Okay, now that that's done, let's save this. And what these four blocks are going to do is basically get this to our MATLAB function. Let's see how to do that. Save again, just in case. Okay, here we have our two previous functions. Let's create a new one. Again, you can basically use a lot of these ones more. Since we're going to be comparing all of these, we might as well copy and paste every single function that we used before. Okay. Sorry. Yeah, let's separate this into sections, which is much easier to run. At the very least to differentiate. This OD45. This is LSIM. Let's call this YY OD45. I no longer care about this, but still let's keep it just in case. LSIM, LSIM. And finally, let's get another function to get Simulink. Now, in order to get the Simulink functions, what we need is to obtain Sim_out. Oops. And let's use the function sim. And we can use the Simulink plot name, which is the name of our Simulink function. And what this is going to do is it's going to assign most of the output functions to this Sim_out. And what we need to do to get them out of here is use sim is equal to Sim_out dot ttsim where sim1 equal to Sim_out sim1 and so on and so on. Okay, now that everything's set up, let's go to plotting. We'll plot two figures, one comparing OD45 LSIM and one of these, and one comparing all these three. Okay, so let's start with figure 1. First, fix first, plot t comma y, what's it called? Yeah, OD45. Again, it doesn't hurt to make this line width 2. Then we use hold on so that this and hold off. That if you use another plot without hold on and hold off, you're going to override it and you're just going to have a single plot in your figure. By doing this, you hold the, all of the plots and you can plot several plots in a single figure. Anyway, let's continue on. T comma YY LSIM. Yeah, that's about right. Finally, sim. Yeah, that's about right. And now let's just use our well-known labels and read on. Let's say this as Matlab. Should we call this? Let's say call this Matlab plot. Okay, now let's see if this actually runs. Nope. Now what happened here is that I didn't write this well. It should be line width and I made a mistake. But as you can see, Matlab tells me the exact line in which it happens, and so I go here and I correct everything. Since I copy-pasted this, that means that this is repeated everywhere else, so I make sure to correct everything. Okay, and so let's run it again just in case, but I could just as well run just this section. Okay, now how do we know if these three have been overridden? Yeah, if you check out the well, initially they seem like they are distinct. The same. They are quite distinct, and that's because we haven't checked out how much the accuracy that the accuracy is left as default. You can change the accuracy so that these three solutions actually coincide, but for now the differences are pretty negligible. Don't worry about it, but still you can see that the three are being plotted one on top of each other. But let's make it much more obvious. For example, we can let this here, and we can instead make it so that this has here, and this is going to change the shape of the lines being used. Okay, let's run this again. Yeah, now you see. You can see the lines being different. That being said, that doesn't still tells us a lot, so let's use a legend. So a legend is going to give a legend of the three plots. So let's say that the first one is OD45, the second one is LSIM, and the third one is Simulink. And yeah, just as always, interpreter LaTeX, font size 14. 11, it should be smaller. Anyway, now let's just run this section. Yeah, and as you can see, three different colors. Anyway, now let's do the same for the three different outputs from the Simulink. This shouldn't be that hard. We just copy here and paste. And now we just put this here, put this here, and put this here. So instead, that will be enough. And now let's call this Simulink 1, Simulink 2, and Simulink 3. Oops, I pressed run when I could have just run the section, but that's fine. This doesn't take a lot. So yeah, now you can see every single thing coincides. And that's about it. That's how you get that's how you bring the measurements from Simulink into Matlab, and maybe that will allow you to better manipulate the plot that you want to present. Before ending, I'd like to go over the difference between transfer function and state space models that we mentioned in the slides. So let's go to a new one. Again, the modeling stuff that I mentioned you before. 0 to 10, fixed step, E4, 0.01. And now let's make this a bit easier. Actually, let's just go over here. And now let's get a transfer function. Yep, this will do. Now let's get this in the same scope. So for the system represented, the equivalent state space representation is going to be 1 over s plus 1. So there is really nothing that we should change here. And as we mentioned, the initial condition is 0 here. We run this. We get the same response. However, if we change the initial condition here, and as you can see, there is really no way of changing the initial condition in this one. Then, of course, we get separate different answers. This is something that you should take into account when setting differences between the state space and the transfer functions here in Matlab. But anyway, that's going to be it for today. If you want to have any questions, you can send them to my email below, and I'll try to answer any doubts you may have had of this lecture. Anyway, thank you for having listened to this lecture, and have a nice day.